So today we're going to be talking about circuits and the most common electronic components that you're going to find in audio electronics. First, let's take a look at this guitar amp here. This is a PV Valve King Royal 8. This is called a combo amp. That's because it's an audio amplifier in the top and it's got a speaker in the bottom. So it's a combination speaker cabinet as well as an amplifier built into that. That's why they call these combo amps. So if you take the screws out and you look inside, this is what the circuit board looks like. Okay? So cool. Now look at this. This is called an assembly drawing. Okay? So this is how it's supposed to be assembled. So it's just a picture of where all the parts go physically. Okay? Now let's take a look at this. This is called a schematic. Now, it doesn't look like the circuit board, and it doesn't look like the assembly drawing. It looks totally different. That's because the schematic is a representation of how all the parts are supposed to be connected electrically, but it doesn't represent the actual placement of the parts in, like, the physical world in real life. It just tells you this capacitor, this leg of this capacitor is supposed to be connected to that resistor that's supposed to be connected to this power supply, etc. Just how it works electrically, how the circuit's designed, that sort of thing. Now, in the olden days, when you bought a piece of equipment, a lot of times it came with a service manual, which included the assembly drawing and a schematic, and they were happy to share that information with you. It seems like since then, two things have happened. One, companies have stolen each other's designs, and two, consumers have used those documents to open up pieces of gear and electrocute themselves, trying to work on it or modify equipment and that sort of thing, and that's been a liability for those companies. So nowadays it's a lot harder to get your hands on service manuals with assembly drawings and schematics like this, but they're really helpful when troubleshooting damaged equipment, because you can sort of say, okay, here's the power supply and the 12 volts I need this thing to work is supposed to come in at this part of the circuit, and then you can take your test tool and see if 12 volts is actually on that part of the circuit, and if it's not, then you got a power supply problem, and so on and so forth. But you're going to have to really work to get these documents anymore. You'll have to call the manufacturer and talk to their service department, and hopefully somebody in there will share these with you. But anyway, sometimes the values of the components that are in a circuit will be written on the schematic next to the part. For instance, if I had a 100 ohm resistor, it would say 100 ohms on the schematic right next to the little representation of the resistor. Those little representations, by the way, those are called schematic symbols. And I'm going to be showing you all the different schematic symbols for these electronic components coming up here in a second. Other times, they won't have the values for those components right next to them. Sometimes there's just not enough space to write all the details about a component on the schematic right next to the schematic symbols. So they'll have a key, usually it's off to the side, or sometimes it's on another page. It's called a parts list. So on the schematic, you'll see a resistor that says it's got a name. They'll call it R1. And then you'll go to the parts list, look up R1, and it'll say R1 equals 100 ohms, quarter watt, 1/4 of 1 watt. And so that's the resistance value and the power handling ratings of that resistor. So you know exactly what kind of resistor you need in that R1 slot. All right, let's move on to actual individual parts. So the first part we're going to go over is, I'm sure you've heard of this, the resistor. Now this one is a fixed resistor. Now if I ask you in class on a test, point to the resistor, or is this a resistor, and there's a picture, I'm going to show you this picture. Now resistors come in tons of different shapes and sizes, but this little peanut on a stick is what I'm going to be referring to as a fixed resistor for purposes of my class, okay? All right. So resistors are designed, get ready for it, to resist the flow of electricity. It may seem kind of vague and overly simple, but that's what they do, and this helps with a wide variety of applications, and you're going to see this everywhere on the inside of circuits and electronics. There's just tons of resistors. So inside this little guy is carbon, and it is going to resist the flow of electricity from the one metal leg on one side to the metal leg on the other side. Now, the amount of resistance that it provides is actually measured in ohms, and this is expressed with the omega symbol. And by the way, and this applies to other measurements for other components, but if you put a K, lowercase k, in front of the omega symbol, you can express thousands of ohms, or kilo ohms, okay? And if you put an uppercase M in front of the omega symbol, you are expressing millions of ohms. Okay, so mega ohms. Sometimes in service manuals and schematics, you'll see the value of a resistor expressed like this. So whenever they put the letter sort of in the middle like this, you're supposed to treat that as a decimal point. So for instance, if I had 2K4 ohms, or if it just said 2K4 and you knew it was a resistor, they're telling you that that's 2,400 ohms, or 2.4 kilo ohms, okay? And likewise, if it said 3M2, that would mean 3.2 million ohms, which would be 3,200,000 ohms. So the resistance value is half the story of a resistor. The other half is the power handling. So how many watts can this little guy handle? This is a 1/4 watt carbon film resistor. So they also have 1/8 watt resistors, which are smaller, and they have 1 watt resistors, which are larger, and so on and so forth. You go up, and some of these resistors can handle a whole lot of watts, but they get bigger and bigger and bigger and start using different materials besides just the little carbon. And like most things, if you put too much power through a resistor, it burns. So you probably noticed those cute little colored bands on the side of the resistor. Those are actually telling you what value resistance this resistor is supposed to be. Let's go over that. Okay, so we need to find the end of the resistor where the colored bands are packed tighter together, and the last band that we're concerned with is almost always silver or gold. So we'll look for that as well. Okay, so we're going to start on the opposite end of the silver or gold band, and those first two colored bands are telling us digits, the first two digits of the resistance value of this resistor. The third band is a multiplier, so we multiply, and it's usually, it's like multiply by 10, multiply 100, multiply by 1,000. It's basically just how many zeros you add. So let's look at this resistor. Here's the color code chart for resistors. Don't worry, I'm not going to make you memorize this. So let's look at this resistor. The first band is blue. So according to our color code chart, that's a 6, okay? And then the second band is red. According to the chart, that would be a 2, so 6, 2, 62. Third band is black. The multiplier for that is 1. And so we have a 62 ohm resistor in front of us. And then the last band, which is gold, is 5%. Now that's called the tolerance for this fixed resistor. So that's going to be a 62 ohm resistor plus or minus 5% of 62. So it could be a little bit more, it could be a little bit less. Now what's the deal with this tolerance? Well, there are, as I said before, tons of resistors inside of electronics, and it's less expensive to quickly manufacture resistors that aren't super precise than it is to manufacture resistors that are super precise. Like a 1,000 ohm resistor is always exactly 1,000 ohms. Now if you're working at NASA and you're building a laser and you need exactly precise resistors, those are available. They are more expensive. Alright, so you guys try one. Here's another resistor. Use the color code chart to figure out how many ohms this resistor is supposed to be. You can pause the video here while you work it out. You got it? Okay. If you got 4,700 ohms or 4.7 kilo ohms with a 5% tolerance, you are correct. Here's another resistor that you're going to see in guitar amps. They kind of look like sugar cubes, and they're designed to handle more wattage. You might also see these in the crossovers of speakers. Here's some other types of resistors. These big ones are called wire-wound resistors. These are good for discharging very large capacitors or cathode ray tube televisions, or just if you have a large charge you need to dissipate without, just shorting it out or touching it, then you can use one of these big wire-wound resistors. They're also useful as a substitute for a speaker when you're testing high wattage guitar amplifiers. If you're afraid you might damage the speaker, you can plug this in instead and won't have to worry about damaging it. These little guys are surface mount resistors. They are very, very, very small. This is how you get all this technology in your pocket with your cell phone, is through the use and magic of surface mount components. And you'll find that there are surface mount capacitors and surface mount transistors, and all those different surface mount components all kind of look the same. They're all just tiny, tiny little rectangles, and they're really hard to work on by hand. Here's two different versions of the schematic symbol for a fixed resistor. The one on the left is the American version, the one on the right is sort of a European version. For test purposes in my class, we'll be going with the zigzag. This is a variable resistor. They're also called potentiometers, or POTS for short. Alright, so for purposes of my class, if I ask, show me a variable resistor, this is the picture you're going to be showing me, because there, again, are a wide variety of variable resistors, and they come in all shapes and sizes. But if I ask you in class, what's a variable resistor, this is what you're going to point to, okay? Okay. So, this is basically a fixed resistor from the two outside legs. That's a fixed resistor. There's two metal legs, a little bit of resistive material that goes from one end to the other, and then it has a third leg with what's called a wiper attached to it that can cheat its way into that fixed resistor wherever it wants along that path of that resistive material. This changes the amount of resistance from the center leg to either of the outside legs, but it doesn't change the resistance between the two outside legs. That's always the same. The value of these variable resistors, which is the total amount of resistance from the two outside legs, is usually printed on the variable resistor somewhere. We can tell this variable resistor is 10,000 ohms total. But like fixed resistors, these are built with a tolerance. For this type of variable resistor, it's probably 10 to 20%. There are two main types of variable resistors. One is linear, and they are marked with a B, just like this one is. And the other is logarithmic, or audio taper variable resistors, and they are marked with an A. Now, with a linear variable resistor, as you turn the knob, as you turn the shaft, the resistance from the center leg to either one of the legs is going to change by 10, 20, 30, 40, 50, 60, 70, 80, very consistently, gradually either increasing or decreasing in resistance. If you're using a logarithmic taper or audio taper variable resistor, you will see the resistance go 1, 2, 4, 8, 16, 32, 64, and with a logarithmic scale, either increase or decrease. A good example of this logarithmic taper is faders. Now, if you look at this fader, this is a variable resistor. And at the top, you can make very small incremental adjustments, plus 3 dB, minus 3 dB, and so on. And then down at the bottom, you'll notice that the adjustments are much coarser. You can make 20 dB adjustments very quickly down at the bottom of the fader. Now, this is because the human hearing is supposed to have a logarithmic sort of pattern to it, and so they use these audio taper variable resistors for volume settings, but like say this logarithmic audio taper variable resistor wouldn't make a very good like pan knob, because you want it to be the same adjustment for the left and the right. So pan knobs would be a good example of when we would use a linear variable resistor. There are also what's called single-turn potentiometers and multi-turn potentiometers. Single-turn, you can get the full amount of resistance from the center leg to either one of the legs by rotating the dial almost 360 degrees. It's not quite a full 360, but you just turn it once. It basically goes around once and you got the whole rotation. There are things called multi-turn variable resistors, which you rotate, 10 times, 100 times, or you just spin it round and round and round for a while to get the full amount of resistance from those two legs. And these are used for more high precision applications. Here are some more examples of variable resistors. All right, let's talk about switches. Here is a switch. This is called a toggle switch because you can toggle it from one position to a second position. You toggle in between the two. Now it's only got two legs. So that center leg will either be connected to the outside leg or not. So this is a single pole, single throw switch. If you were ordering this part, you would see the marking SPST. Here's another toggle switch. This one's got three legs. Now, as you probably have guessed, the center leg will either be connected to the one on the left or the one on the right. This is called single pole double throw, SPDT. Here's another toggle switch. This one's got six legs. All right, check this out. This is exactly like the single pole double throw switch, except it's two switches in one package. Those two center legs will be either connected to the leg on the left or the leg on the right, and the toggle switch switches both of them at the same time. Okay? And now this is called double pole double throw, DPDT. So here's a push-button switch. Now I don't know this for sure by just looking at the picture, but I'm going to go ahead and say that this is a momentary push-button switch. Momentary means that the switch is activated when you push it, and then when you let go of it, it switches back. Okay? That's momentary. It wouldn't be momentary if I push the switch and it actually latches down, and then I have to push it a second time to latch it back. That would be more like a toggle switch. Okay, so let's say that this is a momentary switch. Now, those two legs on this momentary switch are either connected or disconnected. They're either normally closed, which is connected, or open, which is disconnected. All right, so right now I can't really tell from just looking at it, and you'd have to look at when you order the part, you'd have to look for these two designators. If you see a switch on an order sheet and it says NC, that means normally closed. So the switch is normally closed just by itself, and then if you push it, it opens the circuit, disconnects them. But if you see NO, these two legs would be normally open, and when the switch by itself would be normally open and the two legs are disconnected, but if you push the button, that would close the circuit and it would connect those two legs. Okay? Check this bad boy out. This is a rotary switch. So it looks like a variable resistor, but it's not. It actually connects that center pin to each of the outside legs, like one at a time, as you rotate the actuator. That's fancy talk for the part that you grab onto and actually move around, the actuator of the switch. So you'll find that in premium like microphone preamps, they will use rotary switches instead of variable resistors, and that's because of tolerance. They want to get a very precise amount of ohms out of precise setting, because like if you had two microphone preamps and you wanted them to be the exact same volume level because you're recording in stereo, they sometimes use rotary switches with precise load tolerance fixed resistors attached to the legs instead of using like a 20% tolerance variable resistor. Here are some examples of different schematic symbols for different switches. This is a relay. Now it's a switch that's activated by voltage coming in on some of the other pins that are on the bottom there. Okay, so what happens is electricity goes up into the relay, goes through that coil of wire that you see in there. That becomes an electromagnet. It becomes a magnet. So inside that little box, the other legs are attached to a piece of metal that are next to the electromagnet. The piece of metal, seeing the magnet, gets pulled over, touches the electromagnet, which creates a connection, and the switch is activated. Now, you've all played with relays before, believe it or not. Whenever you turn on your home theater system, or I'm sure there's some kind of amp at home, you hit the switch, and it kind of hums for a second, and then you hear click. And then the thing works. But it doesn't work before that switch activates. You'll find this relay is attached to like power supplies a lot. It kind of waits for the power capacitors to charge and the power system to be ready before sending that voltage onto the rest of the device. Now relays can contain more than one switch. So here's some examples of schematic symbols for different types of relays. These are capacitors. And these are the two that I want you to be concerned with as far as my class goes. The one on the left is an electrolytic capacitor, and the one on the right is a ceramic disc capacitor. They use electrostatic fields to store charges. A capacitor's storage potential is measured in farads. Most of the capacitors you'll deal with are measured in microfarads or nanofarads. You'll also need to pay attention to the voltage rating for capacitors. Finally, some capacitors are polarized. They have a positive leg and a negative leg, and you can plug them in backwards, which would cause them to not work and even be damaged. Other capacitors are non-polarized, and you can flip them around one way or the other, and it'll work. Typically, electrolytic capacitors are polarized, and ceramic disc capacitors are non-polarized. Here's their schematic symbols. It's easy to tell on this electrolytic capacitor. This is a 4700 microfarad capacitor, and it's rated for up to 25 volts. And you see that big white stripe with the minus signs on it? That indicates what side of the capacitor the negative leg is on. And usually the negative leg is shorter than the positive leg. Ceramic disc capacitors have markings that are a little trickier, but they work similar to the resistor color codes. It's assumed that the resulting number you get from doing the math here will be in picofarads. So this ceramic disc capacitor is a 10,000 picofarad capacitor. An inductor coil is a very simple device. It's just a coil of wire. But inductor coils resist changes to the amount of current going through them and store an electric charge in a magnetic field. Inductance is measured in henries. Here's a schematic symbol for an inductor coil. Now we'll talk about transformers. Now we've already discussed the transformer that steps down the voltage coming into your home, and there's other transformers within audio electronics. As well as being used for power purposes, transformers can be used in an audio signal path. Sometimes you'll find them in microphone preamp circuits. You'll find people on online audio forums arguing about which transformers sound the best. Now all a transformer is two coils of wire and an iron core. How much voltage is stepped up or stepped down across a transformer is determined by the coils ratio. There may be more or less coils on either side of the transformer, and that's what causes the voltage to step up or step down. There may be the same amount of coils on both sides, which causes voltage to stay the same. It's important to note that DC voltage cannot pass through a transformer. Many dynamic microphones like the Shure SM57 and SM58 have transformers built into the inside that prevents phantom power, 48 volts DC, from getting into the microphone circuit and to the microphone element. Here's a schematic symbol for a typical transformer. This tiny black can on a stick is a diode. It only lets electricity flow in one direction. It has two legs. One marked with the stripe is the cathode, and the other leg is the anode. Electricity can only pass from the anode to the cathode side. Different sizes are available to handle different amounts of power. Here's the schematic symbol for a diode. This little orange guy is also a diode, except he's a Zener diode. He only lets electricity flow in one direction up to a certain amount of voltage, at which point electricity can flow in either direction. Here's the schematic symbol for a Zener diode. This little device that I'm sure you've seen before is an LED, a light-emitting diode. It only lets electricity flow in one direction as well, but it also emits light. This is the most common form of an LED, but there are very, very small LEDs inside many of your television sets. Here's the schematic symbol for an LED. This is a transistor. Transistors come in a wide variety of shapes and sizes, but for purposes of my class, this is what a transistor looks like. They're used for switching and amplification. Here are some other examples of transistors. You may have seen the big silver one before in some guitar amps. Transistors can be made extremely small. In some of the latest i7 CPU processors, there's 1.4 billion transistors. Here's the schematic symbol for transistors. Speaking of CPUs, these are integrated circuit chips, ICs. What happens when you have a common collection of parts like resistors, capacitors, and transistors, and you put them together in many of your products in the exact same way, but you want them in a smaller form factor packed together? You put them together in an IC chip, an integrated circuit. Inside these little packages are little circuits, and the way that you access the inputs, outputs, and power and ground connections of those circuits is through the legs of the chip. Integrated circuits can have a very specific purpose or a very general purpose. To figure out what a chip does, you have to look up the model number that's on the top of the chip. You can also use this number to find the data sheet for a chip, which will tell you which legs do what. Typically, an IC chip will have a mark on the top that will show you where pin 1 is. Then you can consecutively follow that around the chip to find the rest of the pins. Finally, we have the tube. Largely replaced with transistors, this is much less common in electronics today. However, because of the way it handles distortion, it's a preferred choice for guitar amps, as well as some very expensive audiophile music listening systems. Here's some of the schematic symbols you'll find for tubes.